Welcome to today's video on debugging. So debugging is what we call it when we are removing bugs, when we are removing errors in our code. So the history of this is that back in the days, computers were electrical circuits, and what could happen is that insects, bugs got stuck in these circuits, and then the running programs would fail. And even today, when this is not the fundamental problem anymore, we are still calling an error in a program a bug. There's a link to a video here where you can see a bit more about the history, but today we will focus on how you can find and remove errors in your code. So the general advice is that code is always partly a black box. It's hard to know exactly what the code is doing. So what you should always do is to print and plot a lot of results, the end results, the intermediate results, and so on, to convince you and others that the results are correct and sensible. And if an error occurs, the first thing you should think is that it's probably something very simple. We make a lot of very simple mistakes, and they are the easy ones to fix, so look after those first. If it's something a bit more complicated and you cannot exactly find out what the problem is, the first thing you should do is try to locate the line of code where the problem occurs or where the problem is beginning. That's also the benefit of printing and plotting a lot. Then you can see it might return an error at some point, and then you can look at what results did I have immediately before the error. Do they look sensible? Do I think that the error is around here, or when is the error? Try to locate the error. Also, if you have code that runs but gives you unexpected behavior, gives you some result you know cannot be true, then the first thing you should do is try to think about where could this problem come from, which line of code does it come from. In practice, most of the time we are programming, we are spending debugging. We write up some nice programs, some nice functions, some nice classes, and we can run them, and it gives us some results we don't believe in, and we have to dig out what is the problem here. That's the same for everybody. So that's just programmer's life. The first thing you can use in Python to sort of help you with this is you can use assertions. So you can say at some point in your code, after you have run some various code here, I'm defining a variable and I'm taking another variable based on squaring that, and then I'm asserting something. I say, I know at this point that I will have that y should be a positive number. That's what I want the code to be doing. So I'm making this assertion, and then I'm saying it's fine, just continue if that's fulfilled. Otherwise, stop the code and give me this message here. So if I run this, everything is fine. We can see that we have a negative number of -2, but we scare it, so it will be 4, and this is correct. Then that y is a positive number, a strictly positive number. Your task now is to pause the video and try to make this assertion fail. So what we can do is that we can change this to a 0, and then the assertion will fail, and the program will stop, and it will say, okay, this is how it looked now. You didn't want this to happen, so now we're stopping everything. So that's good to have every time you know something about a result, an intermediate result. Make an assertion about it, such that the program stops immediately if there is some unexpected behavior. Sometimes it's a bit irritating that this thing about the program actually stopping. So you can also use what's called exceptions here to handle this. And the idea here is that when code fails, it generates or erases an exception, and you can sort of get around that by trying to do something and then say that you want to continue even though some error has been raised, but you will just want to print what's going on. So you can say here that I can set x to 0, and then I can say I will try something, and I can say that if x is negative, then I have a problem, and I will raise an error, and I will print that this cannot happen. Otherwise, I would say I was successful. But even if this error is raised, then I would actually catch it by saying that if my try block didn't work, then I will catch the exception and I will term it as an E, and I will print whatever that is, and I will let the program continue from here. So if I run this, then it's saying it's successful. So you should pause the video and try to make it unsuccessful. So what we can do here is we can simply put in a -1 here, and we can see that now we will get the error out that x cannot be negative. But the program is continue to run. So if I now here and say I want to print 1 + 1, that will still be going on. So I'm trying something. I will not go into this part because I have raised my error here, but I will continue to do what's afterwards. So that's two good things to know: making assertions and using these try except statements to sort of make your program run robustly in terms of raising errors and catching exceptions. So let's take an example where we think of some code where we have a value for a, and we have a list of x values, and we have some function that takes the list and the value a. Then we start from 0 and we loop through x, and we calculate c, which is x raised to a, and then we are incrementing y, and at the end we will be returning y. And if we run this code, we can see that we get out a complex number. And we didn't expect that, probably. We are just sort of adding numbers together here. Why was this complex? You can try to pause the video here and try to think about what you would do. It's already written down here. You should try to add a print statement. So the idea here is that you temporarily add a line of code which print how does it looks like when you're doing this loop here. So I'm printing each time what is the x value and what is the c value here. And you can see that, okay, it's when x is -1, then it's giving me the complex number. So now I know, okay, it's the -1 thing that is the problem. That's hard to see just from this cell up here, but it's much easier to see once we have the print statement. So it's always a good idea to add print statements and see where problems arises. But you can also have used an assert statement. So you could say that, okay, when you do the loop here, you want to assert that this is a real number. And if it's not a real number, then you will print out what the number is and what the x value that implied this was. And you can see now that it's printing out exactly this message up here for x equal to -1. Because if we have the -1 and raises to some power, then it gives us a complex number. Here I'm also put it inside this try except statement here, such that the code can continue running. I could also have sort of done this with the try except statement, where I raise the value error myself instead of using the assert statement. So I here say that instead of the assert, then I say if we don't have the real value, then I will be printing some message, and then I will be raising a value error. And if I run this, it looks very similar to what I just had above. And of course, if I didn't have this part here, then I would simply get the value error out, and things will stop by here. So this combinations of using print statement, using assert statement, using if and a raise and an exception thing, that is the way forward for you a lot of the time to catch where the errors are. The best thing to do in the end, however, is to find out what should the code actually be doing if this happens. So you might say that, okay, but if we get a negative number, then we cannot do this. So we want to return a nan, another number, because there is no result that we want in this case. So in this case, if we don't have to have the real number, then we will simply just return a nan value. So this is how that works here. Okay, let's go on to the next thing, which are NumPy warnings. So again, we have a list, and we have a function which goes through this list and takes the log of each element. And if we run this code, we can see that we get out a nan in our vector here, and we can see we get a runtime warning that an invalid value was encountered in the logarithm. This is a runtime warning because it was only happened as we run the program. And okay, we can perhaps rather quickly see what's the problem here. It's a -1, and we're taking a log of it, so that doesn't work. One solution, in quotes here, is to just ignore the warning, and you can do that by using this with statement here, where I seem to say that you will ignore all warnings, and if you run this, and the results are the same, but now you don't get the warning printed. You can also control a bit more detailedly which kind of warnings you will ignore, yeah, you can look up the documentation for this rstate function to know that. But this is not really a good solution, right? Because you are just ignoring stuff here. You want to find out what is the best behavior of the program, and the best way to decide what the code should do instead. So now we can actually see, okay, the problem was this about the non-positive numbers, or non-strictly positive. So let's say that if x is less than or equal to 0, then we will just put in -infinity. And then if we run the code, we get out the -infinity, and we don't get again any errors, and it's clear what our code is doing here. So this is the actual solution. But to get back to bugs, then sort of a classic type of bug is scope bugs, and these are related to global variables, which are very dangerous animals. So let's take an example. Let's say we define a function to multiply a value with 5, a variable with 5. So we set a to 5, we define the function, and we say to return a times x. Assume we have many lines of code here, and then we set up the input, and we call this function. So we let y be some vector, here only of 3's, and we take a mean of this. You want to have that for some reason, and we take a mean of using the function on y. And we want this to be a function multiplied by 5, and these are 3's, so I would guess that these should be 15's, and I'm taking the mean, so this should still be 15's. So let's try to run this. It gave me a 9. What is the error here? Try to pause the video and find out what the error is. So one thing you could do here is you could open up the variables panel, and let's see that here, and you can see that, okay, we have our 3 for the y, that looks fine, but we get the result out, but we can see that the a is a 3, right? So okay, so that's the 3 here. Okay, that's what's happening. The a here is 3, and we have 3's, and we are multiplying those, so that gives our 9 here. So the problem here is that in this function up here, this is a global variable. So it's defined out here, and it's trying to find what is the global value of a. When we are down here, then the global value of a is 3. It's not 5 anymore. So that's what's going on. So the way to solve the problem is to make a local variable instead. So adding a as, for example, a keyword argument, and we can delete it up here. If we run this code, then we get the expected results. If now we actually wanted this to be the a that was used in this calculation here, then we should use that as a keyword argument and saying that the local a should be equal to the global a. And then we run, and we get the same result as before, but now it's much more clear why we get that result, because we have this statement here. So the conclusion here is try to never use global variables. It's very seldom that you actually need them, and they can have these personal side effects where if you change the value of the global variable, maybe by mistake, then what the code is doing is changing, even though it might be hard to spot. So use positional or keyword arguments instead of using a global variable. Another type of bugs are index bugs. So let's take an example of that, where we have some integer 10. We create a vector from 0.3 to 8.2 with 10 numbers, and then we set y equal to 9.2, and we want to count all the entries in X that are below Y. So we start with 0, and then we do a while loop. We try to do that. Each time we have a value that's below Y, then we are incrementing it. So we are counting up here. You can see that the code stops. It said that index 10 is out of bounds for axis 0 with size 10. So something is wrong here. It's saying something about an index that we're looking up somewhere, but we cannot do it. Try to pause the video and solve this problem. There's many solutions here. One solution is to simply say, okay, what the problem here is that of course we cannot look up if this I is too big. So actually we want to continue while this is something that's going on, or we can simply say that we want I to be smaller than the size of X, and then this. So we will only count upwards in these cases here. So let's see this ran, and we can now print I at the end, and we can see that this is printing 10 here. So that is, at some point we will hit the 10, and now this will not be fulfilled anymore, and therefore the while loop will stop. An equivalent way of doing this is that we can say that if we have that Y is larger than or equal to the size of X, then we want to break out of the loop. And we get the 10 again. So there's many different ways of solving this, but as soon as we do some kind of lookup in a while loop, or where we in some way are changing the index, we need to think about if we at any point looking up in the vector here outside the size of the vector. So that's a good thing to always be checking, and an often error, or oftentimes found error. Okay, so until now we have sort of used printing and sort of assertions and these try except stuff to try to find out where our errors were. We can also use something in VS Code called a debugger. And a debugger is a special way of running your code where it's easier to find errors. So let us look at an example here where I'm defining some function that takes in an X. It computes a Y, that's X minus 5, and it computes Z, that's C, that's equal to X, and it computes the log of the product of these. So I can define this function, and then I can set X to 4, and I want to compute f of X, and I can print out the result here. I get an AND, and I get a runtime warning of an invalid value encountered in the log. And now I want to understand why this problem arises, and it's a good example of how we can use the debugger. So we can go to the first line of this function, and we can go out here and we can click one time, and we can add this dot, which is called a breakpoint. You can also just press F9, and then you will get this breakpoint. And then you can go to the cell here where the problem is arising, and then you can click out here and you can click debug cell, and you can use this keyboard combination. And if you do that, then it sort of starts running this as a debugger. So a lot of things happened on my screen here. You can see that the left panel changed, and now it's telling me which kind of variables am I having now. And we can see here that I'm having that the X value is 4, and that I'm now in this part of the function here. And now I can sort of move forward in this code here by using the panel that's up here. I can also press F10, and I can do these kind of things. But if I press up here, then you can see then it continues one more line, and now we can see okay, now we have put an X value of 4 and a Y value of -1, and now we will continue the Z value. So okay, now we can see that we get a negative value, and okay, that's where the problem in the log is. So now we can sort of see what's going on inside the function, and in this way sort of investigate that. We also have access to sort of a small panel down here where we can try to do various kind of things. We can put in the Y and see that it's actually -1. We can also, if for some reason that's not important here, but we can sort of do small calculations and whatever. We can now continue. So now we've understood where the problem is, and we can sort of just continue running, and we can now set is 4, and now we're at the return statement. So once we have done that, then it will go out here, and now we will be out in the notebook where there's other variables. There's a lot of other stuff here, and we can just continue, or we can at some point press shift F5, and then we sort of stop the debugger. So this is sort of a way that we can go into a function and see what the problem is by adding this breakpoint and running this debugger. So that can be a very efficient way of finding out what the problem is, sort of deep inside of your code. There's a lot of other things. Now I'll remove the breakpoint again because we don't need it anymore. There's a lot of other things you can use the debugger for. You can sort of, instead of this sort of just stepping over, you can, for example, add a breakpoint here, and then you can debug the cell. And now if you just press F10, then it just continue and sort of just go through it all, and you don't learn a lot. But you can instead say debug cell, and then you can use this step into instead, where now it will actually step into this function, and you can then go through the lines in this way here. And there's many other things where you can use the debugger for. So try to do that on your own, and see more details from the VS Code developers here. This also works if we have if we do this with modules. So let's import a module here, and let's see that we get the same problem as before with this G function here. And now I want to solve this. I want to understand where the problem is. So I can go into my